Example 22.8 is going to show us how to find a volume of revolution when we don't have necessarily a solid. Maybe there's some region that's cut out of the middle. First, let's understand this region that we're going to rotate by drawing these two functions, y is equal to x squared plus 1 and y is equal to 3 minus x. That's a better way to say that. So let's sketch these two functions. There's your y-axis, here's your x-axis. X squared plus 1 looks something like this. Oops. No, it is not. It's shifted off the x-axis by 1 unit. It looks something like this. And the line 3 minus x, or minus x plus 3, has a negative slope and a y-intercept of positive 3. Okay, so we're going to take this region and we're going to spin it around the x-axis. So the way that we're going to do this is by the method of washers. We're going to take these lines and we're going to spin them in circles. So you can see that it's going to have an empty space, because when I spin that big circle around a circle, I need to cut out this green circle. And that's going to generate a washer. So let's call this big radius capital R, and the small radius, the green radius, lowercase r. So the big circle has an area that's going to be dependent upon x, right? If I draw my big circle over here, it's different than if I draw my big circle over there. So it is a circle, so it's pi r squared. The radius is given to me by this top function. So y is equal to 3 minus x. So simplifying this a little bit, we have 9 pi minus 6 pi x plus pi x squared. These little green circles that we're going to cut out of these have a radius given to us by from the x-axis to the bottom curve. So the area of these circles are pi r squareds, where the radius is given to you by the bottom curve, x squared plus 1. So simplifying, we have pi x to the 4th plus 2 pi x squared plus a pi. So how we should think about this is we're taking the big circles and subtracting away from it the little circles. So once we do this, we have pi r squared minus pi little r squared. We've already done all the work. This becomes pi times 8 minus 6x minus x squared minus x to the 4th. Just by taking the big circle and subtracting the smaller circle and factoring out a pi. So this is how we find the areas of those washers. And now we're going to scan these washers from this x value, where they intersect, to this x value, where they intersect. And we can find their intersection points by setting these two functions equal to each other. A quick quadratic formula tells you that this is -2 and this is +1. So we are going to integrate from -2 to +1 the areas of these circles, which the pi can come out as a constant, and we're integrating 8 minus 6x minus x squared minus x to the 4th. An antiderivative will be 8x minus 3x squared minus 1/3 x cubed minus 1/5 x to the 5th, which we will then evaluate from -2 to +1. So skipping all the gory details, if you take this antiderivative at the upper bound of 1, you get a 67/15. And when you take the antiderivative and evaluate it at the lower bound of -2, you have a -284/15. So by simplifying, you end up adding 67 to 284 over 15, and you find 117 pi over 5. So volumes of revolution in general might have regions cut out from the center, and you effectively just generate washers by finding a big circle and subtracting the inner circle, and then integrating that washer between your two bounds.